Hello friends, welcome to today's lecture ILD. Myself, Mr. Y.S. Patil, Department of Civil Engineering, Sharad Institute of Technology, College of Engineering, Yatra. In this lecture, we see one problem. Draw a ILD for RA, RB, shear force at X, shear force at Z, bending moment at X and bending moment at Z. It is a simple problem having a overhang beam, that is P, A, B and Q. AB is a support apart from 10 meter from each other, and from that AP distance is 2 meter and BQ distance is a 2 meter. So basically first we calculate ILD for RA. Means if I want to draw ILD for RA, first of all I know the value of RA. Means if you want to calculate RA, you should taking moment about B. So taking moment about B, and before this assume 1 kilonewton force unit load at a distance of X from point P. This P is the origin. So from this 1 kilonewton force at a distance, this is a movable load. So X is a variable. 1 kilonewton force acting at a distance of X from point P. So if I want to taking moment, if I want to calculate RA, so taking moment about B. So taking moment about B with respect to B, I want to calculate RA. So moment of this RA is clockwise and distance from point B is 10 meters. So RA into 10. Then this 1 kilonewton force, the direction of the moment with respect to B point is anti-clockwise, and from B point to this load is distance, means that this is a PB distance is 10 plus 2, that is 12 meter, and I want to distance from this point load to this point B. So distance is 12 minus X and the force is 1 kilonewton and direction of the moment is anti-clockwise. So plot on this side, this is the 1 kilonewton force and distance is 12 minus X is equal to RA into 10. So RA is equal to 12 minus X divided by 10. This is the value of RA in terms of X, and that X is a variable. So plot a table point X and RA. Means suppose this point load now at the point of P, then the X value is 0 because the X measures from point P. So P is equal point P, X is equal to 0. Put up this X is equal to 0 in this equation. 12 minus 0 divided by 10, then RA becomes 1.2. Then next, this point load moves from point P to A, means now your point load at point A. Then X value from point P to A is a value 2 meter. So X is equal to 2. Put up this X is equal to 2 in this equation, that is 12 minus 2 divided by 10, that is 12 minus 2, 10 by 10, it is 1. Then next, this X moves from point A to B. Now this PB distance is 10 plus 2, that is 12 meters. So 12 minus 12, 0 divided by 12, 0. So when load at point B, X become 12 and that RA become value is 0. Then load moves to point Q. So this distance PQ is 2 plus 10 plus 2, that is 14 meter. And put up this 14 in this equation, 12 minus 14, that is minus 2 divided by 10, that is minus 0.2. So this is the coordinates for ILD RA. Plot these coordinates, positive values plot upper side, negative values plot downside of the baseline. So at P, this is 1.2, at A, this is 1, at B, 0, and at Q, minus 0.2, means minus 0.2 plot downside. So join all points, and this is the ILD for RA. Means when load at A, apply unit displacement at A point. This is the unit displacement, and by using the similar triangle properties, we can find out easily all values. Then next, ILD for RB. when you calculate ILD for RB, you should know value of the RB. So taking moment about A. Once again, this is the unit load applied at a distance of x from point P. With respect to A, taking moment, first this point load moment, this is the clockwise now. The distance from point A is, this is the total x, and I want to distance this A to this point load. So x minus 2. This is 1 into x minus 2, and RB is anti-clockwise, and distance from that A to B is 10. So RB into 10. Then RB is equal to x minus 2 divided by 10. Once again, consider all points and all x values and calculate RB value. First of all, starting with P point. When load at P, the x becomes 0. So x minus 0 means x is equal to 0. 0 minus 2 divided by 10 is minus 0.2. Then load move up to A, that is now x is equal to 2. Then 2 minus 2 divided by 10 is equal to 2 minus 2 is a 0. 0 divided by 10 is become 0. Then load moves up to point B. Now the value is, x value is 2 plus 10, that is 12. So 12 minus 2 is equal to 10. 10 by 10 it's become 1. Then load moves up to point Q. Now PQ is a 2 plus 10 plus 2, that is 14. Put up this x is equal to 14 in this equation. 14 minus 2, that is 12. 12 divided by 10, 1.2. Once again, consider all coordinates and plot positive value upside of this baseline, negative value downside of this baseline. So at point P, value becomes minus 0.2. So plot downside of the baseline. At A 0, at B 1, that is positive, this is the 1, and at Q 1.2, this is the 1.2. Join all points, and this is the ILD for RB. Then next, ILD for shear force at X. This is the X point. X is a X point at a distance of 3 meters from point A. So first of all, this due to this X, the beam is split into two parts, that right of the X and left of the X. First of all, consider when load lies between P to X, means this is the load 1 kN at a distance of X, and this load lies between only P to X. So number of forces on the left side of the X is this 1 kN, and second one is a RA. And on the left side of the X, on the right side of the X is RB. Then consider minimum force side. So consider right side of the X. So shear force at X is equal to, the number of force on the right side is RB, and the direction of the RB is upward, and right side upward force consider minus sign. And we know the value of the RB is x by 2 divided by 10. So shear force at X is minus x minus 2 divided by 10. And this equation is only valid up to when load lies between P to X, means limits for this X is 0 starting point and X is a 3 plus 2, that is 5. Means this is the limits for X 0 to 5. In that, put up all values in this equation. First, P is equal to 0. Put up P is equal to 0 in this equation, that is 0 minus 2 divided by 10, that is 0.2, and it become, minus minus plus, it become positive. Then load comes at point A. So X is equal to 2. So 2 minus 2, it become 0, and 0 divided by 10, 0. Then next, load moves up to X. Now X is equal to 5. That minus 5 minus 2, that is 3. Minus 3 divided by 10 is minus 0.3. Then if the load crosses this X point, this equation becomes not, means the values from this answer is not correct. So you want to need say new equation. So now when load lies between x to q, means load comes in this part, this crosses x point, that x to q, and the limits for this x to q is, the x limit is a 5 from point P and q is a 14. So x is a 5 to 14. When load crosses this x point, now number of forces on the right side is now 2. This is unit load 1 and RB. And number of force on the left side is 1, only RA. So consider left side. And we know the left side upward force consider positive. So force is that RA. And the RA value is 12 minus x divided by 10. So this is the equation when load crosses point x, or load lies between x to q. By using this equation, calculate all values, that is x, b and q. The x value for point x is 5 meter. So 12 minus 5 divided by 10, that is 12 minus 5, 7 divided by 10 is 0.7. B is a 12. So 12 minus 12, 0, 0 by 10, 0. Then q is equal to 14. So 14 minus, so 12 minus 14, that is minus 0.2, minus 2 divided by 10 is minus 0.2. Considering this all P, A, X, B, Q, all values, put up or plot this value. So at point P, 0.2 positive, plot upside. At point A, 0, remain on the baseline. At point X, minus 0.3, so plot on the bottom of this baseline. At point X, 0.7, plot upside of this baseline. At point B, 0, once again it lies on the baseline. At point Q, minus 0.2 on the bottom of this baseline. Join all these points by straight line, and this is the ILD for shear force at X. See here, at point X, it becomes two values, that is minus 0.3 and plus 0.7. But if you calculate this starting point to end point, 0.7 plus 0.3 becomes 1. I mean, this is the shear force. Whatever the values it converted becomes unit load. So this is the shear force at X. Next, ILD for bending moment at X. Once again, consider when load lies between P to X. When load lies between P to X, the left side of this X number of forces is 2, this unit load and RA, and right side 1 and only RB. So consider right side of this force. So taking moment about this point X. So bending moment at X is equal to, consider right side. Number of force is 1 RB and the distance from XB is a 7. Because this is a 3 meter, so 10 minus 3 is a 7. And we know the value of the RB is x minus 2 divided by 10 into 7. Once again I repeat, this equation is only valid up to when load lies between P to X. Whenever the load crosses this point X, this equation will be, or whatever the results or whatever the answer, it will be wrong one. So this equation is only valid up to when load lies between P to X. So once again calculate all points P, A, X. Put up X is equal to 0 in this equation. The value becomes minus 1.4. Put up X is equal to 2. The value becomes 0. Put up X is equal to 5. The value becomes 2.1. Then when load crosses point X, the next solution will be like this. When load lies between X to Q. Now limit is 5 to 14. So bending, taking moment. Now when load lies between X to Q, number of forces on the right side is unit load 1 and RB. Second. So number of forces is 2 and number of forces on the left side is 1. So bending moment at X considering left side. So RA into perpendicular distance is 3. and we know the value of the RA, that is 12 minus x divided by 10 into 3. Now calculate all values, that is x, b and q. The x distance is 5. So put up this 5 in this equation. The answer will be 2.1. Then put up x is equal to b point distance is 12 meter. So 12 minus 12, 0, 0 divided by 10, it becomes 0. Then next, at point Q, x is equal to 14. Put up this 14 in this equation, you got minus 0.6. By considering this all values or all coordinates, plot on this diagram. So first of all, minus 1.4 minus indicates you should draw bottom of this baseline. Then at point A, 0. Then at point X, it will become 2.1. In second case, means x is equal to 5, it become 2.1, means in bending moment, if you calculate bending moment at x by considering right and left or considering two cases, the bending moment value doesn't change, so remain as it is, 2.1. At point B, 0, and at point Q, minus 0.6, means minus 0.6 bottom side. Draw this sketch. Upside bending moment value positive, downside bending moment value negative. This is the ILD for bending moment at x. Then next, ILD for shear force at z. This is the z point at a distance of 1 meter from support B. So once again, you should split into two parts, z right and z left. Suppose when load lies between P to Z, the number of forces on the left side of the Z is Ra, this 1 kilonewton force, and Rb, and number of forces on the right side of the Z is 0. So we consider when load lies between P to Z, consider right side of the Z. When load lies between P to Z, consider right side of the Z, then shear force value at Z is equal to 0 because no load on that ZQ force, ZQ span. So when load lies between P to Z, it becomes shear force at Z is equal to 0. Then when load comes at point Z or crosses the Z and lies between Z to Q, so number of forces on the right side is now 1 kilonewton because now load comes up in this ZQ portion, and number of force on the left side of this Z is RB and RA. So consider minimum forces side, that is right side of this ZQ, and this force is 1 kilonewton force. So SF at Z is equal to 1, means when load crosses this Z point or up to Q, the shear force become 1 kilonewton and it is a constant. This is the sketch for shear force at Z, ILD. Okay. Then next, draw ILD for bending moment at Z. Once again, split or divide into two parts, that is Z right and Z left. Suppose load lies between P to Z. The number of forces on this left side of this Z is 1 kilonewton, Ra and Rb. So, and number of force on the right side of this Z is 0. So I consider right side of this section, means bending moment at Z become 0. Then next, when load come at point Z or crosses this Z point and load lies between now Z to Q. So bending moment value is 1 kilonewton force downward. With respect to Z, moment is clockwise, and we know the right side clockwise moment is negative. So minus 1, it is a force, and perpendicular distance is, this load comes in the span ZQ. So x minus this PZ distance, that is 13. So x minus 13. So bending moment at Z when load lies in between Z to Q is -1 into x minus 13. So this equation is only valid when load crosses point Z. So calculate Z and Q coordinates. So when load comes at Z, the x value is 13. So 13 minus 13, 0. So bending moment at Z becomes 0. Then next, when load lies on at point Q, the PQ distance is 14. So put up this 14 in this equation. 14 minus 13, that is 1. 1 into -1, -1. So coordinates is 0 and -1. Just some checkpoint, that is when load at Z, and if I want to bending moment at Z, so bending moment at Z becomes 0 because it having load but there is no perpendicular distance. That's why the bending moment value at Z is 0. So consider these coordinates 0 and -1. Plot this sketch. -1 means you should plot on the downside of this baseline at Z 0, and at PAB it becomes 0 because bending moment at Z is equal to 0. This is the ILD for bending moment at Z. Whatever you calculate reactions, shear force, bending moment for ILD, you should apply unit load 1. This is a solution for overhang beam, and ILD for RA, RB, shear force at X, bending moment at X, shear force at Z, bending moment at Z. Thank you.